Okay, today's talk is called the Neurosymbolic Approach to Counterfactual Fairness by Xenia Heilmann. I hope that I pronounced it correctly, but sorry if not Xenia. Um, and Xenia is a PhD student in Germany, and her special focus of her research is on neurosymbolic approaches. If you're interested in more details, here is her website and a link to the paper that she's going to cover today. As usually, your comments, questions are welcome on those three platforms: Discord, YouTube, and LinkedIn. We are planning to monitor all three of those. And next week, we are going to have Ruipeng Leo, who is going to present his research next week. And with this, I pass it over to you, Xenia.
Yeah, thank you, Olga, for the nice introduction. Nice. Okay, then let's start. So I will tell you today something about our paper, A Neurosymbolic Approach to Counterfactual Fairness. So this is joint work with Chiara Manganini from the University of Milan. She's a philosopher, and also with Mattia Cerato, Leonard Kestel, and Vaishak Bell from Johannes Gutenberg University Mainz, so also the university I'm in, LMU Munich, and the University of Edinburgh. Yeah, so let's start with a small motivation why fairness in machine learning matters. And I brought you this news article, which just came out a few days ago, and I found it very fitting to today's topic. So it was a newspaper article by the Financial Times, but also other newspapers reported about the study. And it's a study which, this newspaper titled that the study found out that AI tools lead to clear racial disparities in job hiring. And the study by a group in Stanford, they found out that there were clear racial disparities when they looked at job hiring, AI-based hiring tests. And what they did is that they analyzed individual roles where people applied to, and they found that 1 in 10 of the positions in the dataset demonstrated adverse impact against Black applicants, and 1 in 20 roles did the same for Asian applicants. And what does this adverse impact mean? It's a term used by the US federal agencies to describe a selection rate for any race, sex, or ethnic group that is less than 4/5 of that of the most selected grouping. And articles like this, they come up every now and then, and it just shows us, I think, very clearly that with every AI tool we develop, we always need to keep in mind that it can actually discriminate against specific groups. And this is especially important to look at when you look at AI tools which are deployed in high stakes settings. So as you just saw, this was job recruitment, but also other high stakes domains could be like credit scoring or recidivism prediction. And when we look at fairness in machine learning, what we mainly look at is we look at detecting bias. So we look at the data sets to find out is there maybe a bias in the way this data was sourced, or or questions were asked to kind of generate this data set. Is this data set maybe biased by different other reasons, or is it, or maybe also we look at machine learning models which are already trained, and we want to know, is this like a machine learning model which might discriminate against a specific group or not? And then on the other hand, what we also look at is mitigating this bias by trying to implement something maybe in the training pipeline of our algorithms to mitigate this bias which was in the data. And important is to really say we try to mitigate it, because we never, the question is always, does this really work, what we try as a method? And how do we find out if it works? Well, we somehow need to measure how fair a machine learning model is. And for that, there are some algorithmic fairness metrics. And they mainly distinguish, so these metrics are mainly grouped into two groups. So we have group fairness metrics and individual fairness metrics. And I shortly want to talk about both of them, what they mean. Let's start with the group fairness metrics. So I only want to show you one example of those today because this will not be the main topic of the talk. But group fairness metrics, what they look at is they look at groups of individuals. So for example, we have this fairness metric of demographic parity. And what demographic parity looks at is for example, the acceptance rate over the sensitive groups I look at, is it the same? So in this example here, we have a group of males and a group of females. And this blue is like an acceptance rate, for example, for like for law school. And here we see that for the males, we have an acceptance rate of 0.6, for the females of 0.4. So you already see there's like a difference between those two groups. And this is called demographic parity difference. And this in this case would be 0.2. And then we already know, okay, so this is definitely not the same acceptance rate. Maybe we need to investigate a little bit if our algorithm really is fair across these two, male and female, so these two groups. What group-based metrics cannot do is look at individuals. So let's imagine the following. So let's look at this female here. So she didn't get accepted to law school. And let's say, okay, we look at the data point and we see, okay, she has a good education. She was good in school. And then we look at this male who actually got accepted, and we see, oh, but he was as good as this female in school. So what happens here? And this is something you cannot see with group-based metrics. And that's why we also have these individual fairness metrics that actually look at individuals in the data set. And one of these individual fairness metrics is counterfactual fairness, which will be the topic today. And what counterfactual fairness asks is, would I be treated the same way had my protected attribute been different? So protected attribute in our example would be the gender, so female. And then the question would be if I would have a different protected attribute, or if I would be male but nothing else would change, would my prediction have changed? And the formal requirement for this question was by Kushner et al. In 2017. And this is exactly this formal requirement of the question. So we have here the prediction, the sensitive attribute S, and all the other attributes of a data point X. And we want that this side of the equation is the same as this side. And the only difference between those two is that here, for the prediction, we intervene on the sensitive attribute by plugging in a different value of our sensitive attribute. So as a example here down here, so let's think about again the example that we just had. We want to be accepted to law school, and this is our data point. And then when we intervene on gender, we get this data point, which is called a counterfactual, and we ask, does the prediction change? And if you look very closely on this, what happens by generating this counterfactual here on the side, so by intervening on gender, is that not only the gender changes, but also the LSAT and the GPA score. Now the question is, why does this happen? And this is because LSAT and GPA are actually influenced by the gender. So counterfactual fairness takes account of this. So for maybe a little bit more clear example is if you have a female who is of average height, so maybe 165 centimeters, meters, and you intervene on gender and do not change the height of this data point, then this would maybe, as a male, would not be an average height of a male, right? It would be maybe an outlier. And this is why the influenced attributes also need to be adapted. And this is exactly what counterfactual does. It requires knowledge because of that of the causal model M, and I don't want to explain in too detail what a causal model is. You can imagine a causal model to represent the data generation process, and if you know this causal model, you can actually generate these counterfactuals. And if we put this into words, so we have the counterfactual requirement in this case that a female applicant's predicted admission status should remain unchanged if counterfactually she had been male, and then including appropriate adjustment of all causally influenced features, which in our case are LSATs and GPA. And then in the example we have, so this would be counterfactual fair if both would get if both data points would actually get a positive admission status. Okay, so this is the topic today, counterfactual fairness, and the question is why did we combine this with the neurosymbolic method? And there is some existing work on group-based fairness integration into logic tensor networks by Wagner and Davila-Garcés. And but there's nothing on counterfactual fairness, so we thought we would take a look at this. And what is very nice about integrating this into a neurosymbolic framework is that we can be very transparent and audible, very transparent, and later on you can audit what we actually did by integrating this fairness. So this is what I said before. It's very important to actually, after the training has finished for your model, to really know what did you do, did this really work? And this is something that is very nice to do. Okay, so let's see how we did this. So we worked on logic tensor networks. And the key idea by logic tensor networks, I think most of you know them, so I will only target this very shortly, is that logic tensor networks, they integrate a fully differentiable first order logic with fuzzy semantics, and they ground logic into the tensor space by a grounding G. And we have constant variables, functions, and predicates, and these are grounded onto tensors of real numbers. We also have connectives, which, so this is specific to our method, which are defined like this. I'm not going to read this out. And then we also have quantifiers. So we have the existential quantifier and the for all quantifier. And here you can adjust this P. So, and then what you do is you have some truth values for axioms you can make, and these are continuous. And then when you train this logic tensor networks, you want to maximize the satisfaction of a knowledge base K of axioms. And the satisfaction is like an aggregate over all the truth values of your axioms. And how these axioms look, we will see this in a second, because this is exactly how our pipeline actually works. So we have this huge axiom block in the middle, but we start with a data, and from this data we generate counterfactuals. I will explain how this works in a second. Then we have our axioms here. I will also explain them in a moment. And then we train our model, and we stop training when we reach the specific satisfiability. And during the training, we also extract imbalances and counterfactual explanations. And these counterfactual explanations, what this means exactly, I will also explain. Okay, so what we will do now, we will just go from, this should be left to right. And then we will, I will explain all these steps to you. So let's start with the generation of the counterfactuals. We did this with causal normalizing flows. And why we need to do this is because, so we have, like I already said, we need this causal model M. But the problem is that this causal model M is unknown in practice. So that's why there are some methods like the causal normalizing flow method by Javaloy et al., which is a deep generative model that approximates this causal model M from observed data and a causal graph. And the causal graph is what you can see here on the side. So this is the causal graph for the example we had all the whole time for the law school data set. And this you read like this. So everything that is in this square here is causally influenced by everything that is connected to the square. So in this case, gender and race. And this causal graph is obtainable from domain knowledge. So we didn't need to invent this. So this was already given. And with this causal graph, and like I said, observed data, we can generate counterfactual samples with this causal normalizing flow method. So what we get out is for each X in our data set and for a specific sensitive attribute, we can get out a counterfactual sample. And these we need as input to our axioms. And our axioms we will look at now. So we have 3 kinds of axioms. The first ones are just accuracy axioms. We need those so that we can actually have a model which is also occurrent, because because it doesn't make sense to have a model at the end which is good at being counterfactual fair, but otherwise not usable. So for the binary prediction, what we have is that for all X which are in our which have true positive labels, we also want that our classifier D has a positive outcome, and the same for the true negative labeled data points. Here we want, of course, that the classifier also predicts them negatively. Now, because we also wanted this to work for score-based predictions, we had to define an equality predicate, and this equality predicate looks like this. So it kind of looks how much the prediction, so the predicted score and the true score, is apart from each other. And with this equality predicate, we can then also define an axiom. So we want that for all X in our data set, we want that the prediction and the true label is not that far apart. Okay, so now for the counterfactual fairness axioms. So what we encoded in the counterfactual fairness axioms is exactly the definition of counterfactual fairness that you saw before. So we want that for all individuals in our data set, we want that they're counterfactual with respect to the sensitive attribute, that these data points and the counterfactual gets predicted in the same way. And now what I want to say here very shortly is that you can have more than one counterfactual for a data point. So for example, imagine that your sensitive attribute is race. Then of course you have like one counterfactual for each of the different races you have in your data set. So this can be more than, so x prime can be more than one. So the counterfactual can be more than one. And if we satisfy this axiom, if the satisfaction is 1, then we can actually say that this model is counterfactual fair for all data points. Sorry. Okay, let's go back. And what we saw when we added these counterfactual axioms, counterfactual fairness axioms, is that because we defined them over the complete data set, that they were satisfied often at a very high level. But if you looked at how this worked, then you saw that very small sensitive groups in the data set actually had a very bad counterfactual fairness, and majority groups had a very good counterfactual fairness. And that's why we integrated subgroup counterfactual fairness axioms, which take this into account. So we added those to improve fairness evenly across all subgroups. And what we did here is that we just added one counterfactual fairness axiom for each subgroup in the dataset, and these subgroups can be defined as one-ones in a way, so you can use combinations of sensitive values, like all values from gender and race in combination. But you can also use, if you have an application-specific subgroup you want to look at, you can also use this as input for these subgroup axioms. And the last part, what we did was counterfactual knowledge extraction axioms, and these work on counterfactual explanations. So I will show you what this means. So counterfactual explanations are defined as the minimal set of changes to a data point X sufficient to obtain a positive outcome. So so what this means is that if we have a data point which is predicted negatively, you get a set of changes that you can do, and if you do these, you will obtain a positive outcome. And these changes are interventions on the causal model M. So yeah, so for this and for these counterfactual explanations, you can split your features into two types. So you can split them into actionable features, so features which can be changed, like job, education, etc. So for job, you can, for example, do maybe a training, and for education also, etc. But then there are also features which are immutable, so features which cannot or should not be changed. And let's look at an example. So what we wanted to, so for example, this is a person who is female and who didn't get a job interview, and her marital status was not married. And then as a counterfactual explanation, this person got that if you change your marital status to married, then you will be accepted for a job interview. And this, of course, is very undesirable to get as a counterfactual explanation, right? Because it suggests that you have to change an immutable feature. And we looked at these undesirable counterfactual explanations. And what we wanted to do is we wanted to find out, does the model suggest that you need to change an immutable feature to achieve a positive outcome? And if the model suggests this, can we see an imbalance across sensitive groups in the frequency of these undesirable explanations? So for example, let's say that you get said that you need to change your age, and maybe for males, this is very unlikely or very seldomly the case that it is said, but then for females, it's said very often that you should change your age. And this would then be like a really big imbalance. And for this specific case, we would generate an axiom to suppress these counterfactual explanations. And what we have in this axiom is that we look at our data points which are predicted negatively and are in our sensitive group that we look at, and we generate a counterfactual for the feature which was said that you need to change it, and then we want that the prediction is the same at the end. And this kind of encodes what we just said, that we do not want that this immutable feature is given as an explanation. And this is what is encoded in this axiom. And what we did is we added these axioms iteratively. So we added one axiom, then we trained for several epochs, like 500, and then we checked again, did this help or not? Do we need to add another axiom? And then we would add this. And this, in our case, we did it automatically, but you could also use a human in the loop in this case. Okay, so let's get to the experiments. What we looked at were the following data sets. So we looked at adult compass in law school. And as sensitive attributes, we had, for adult, we had gender. So this is binary in this case. For compass, we had race. And for law school, again, we had gender, which is also binary in this data set. And then we had some baselines. So we had the causal normalizing flows, which I will call, to make it shorter, CNF in this case, from now on. And the causal normalizing flows I already explained, that we use them to generate the counterfactuals. And as a baseline, what we did is we trained a multi-layer perceptron that we also used in our as our model on the augmented counterfactual data, and so just the data and the generated counterfactuals. And then we had a generative adversarial network and also a disentangled causal variational autoencoder as baselines. And what is kind of specific for counterfactual fair models is that all these baselines generate their own counterfactuals in a way. And what I will show you today is only the results for all the all methods evaluated on the causal normalizing flows generated counterfactuals. So what we evaluated was counterfactual mean squared error. So this is just a metric to measure how counterfactual fair model is. And the lower this error is, the more counterfactually fair model is. And then for adult and compass, we also measured accuracy, and for law school mean squared error. So let's look at some results for the adult data set. So what you see here is the results for the counterfactual mean squared error in different axiom settings. So we have in blue the pipeline only with accuracy axioms, in orange the one with accuracy and counterfactual fairness axioms, and in red accuracy axioms and the subgroup counterfactual axioms. And what you can already see is that by adding the counterfactual fairness axioms, we already strongly improve counterfactual fairness for most subgroups. Here you can see one subgroup where it doesn't improve. But if we add these counterfactual fairness subgroup axioms, then we can correct this. So this is, as like I already said when I explained the subgroup counterfactual axioms, that here this is like a very, very small group, and that doesn't work that well just adding a global counterfactual fairness axiom, but you really need these subgroup axioms. Yeah, and when we compare to baselines, what we see is that the other methods normally have a higher accuracy and mean squared error, but in terms of counterfactual fairness, we are better than them in all datasets. So our method kind of has an accuracy trade-off, but what I found very interesting is that we actually see, so here in the first row, actually see an improvement of the accuracy when we add counterfactual fairness subgroup axioms. And here, and then here's the next result for the counterfactual knowledge extraction axioms. So again, so the first question is always which undesirable counterfactual explanations are more frequent across which subgroups. And what you can see here on the compass dataset is that for the black subgroup, age gets outputted very often as a counterfactual explanation. And this is very much higher than for the white subgroup. And so in this case, we added an axiom, a counterfactual knowledge extraction axiom for the black subgroup and age as the attribute. And then this is the outcome. So this blue, orange, and red you already know. And green is then adding the counterfactual fairness axioms and the counterfactual knowledge extraction axiom, and then pink is adding this on top of the subgroup counterfactual fairness axiom. And what you can see here for the group where we applied it to, especially for the young, under 60 aged ones, that this improved counterfactual fairness. What you can see on the other hand, and this is on this plot again, is that when we added this axiom, so these are these not colored columns, that some other explanations went very up high, and this you can, for example, see here on the priors count. So after adding the axiom for age, we see that priors count is often outputted as a counterfactual explanation. And the last thing I want to show you is that we also tried doing postdoc queries on our model. And one query we tried out is the following. So is there a similar individual in my subgroup with a different outcome? And this is very interesting if individually you want to find out if you were treated fairly by the algorithm. And here you can see one example. So this is the query in this row here. And as an answer, we show one data point here. And the satisfaction level kind of says how many data points altogether there can. So this is kind of the group. The higher the satisfaction is, the more data points there are which actually are similar to you but have a different outcome. And what we can read out of this, especially these two examples here, is that the sample with a positive prediction, so for adult a salary higher than 50K, is 24 and married rather than 23 and unmarried. Okay, so let's conclude. So what we kind of saw as advantages of this neurosymbolic approach to counterfactual fairness was firstly the transparency. So we could encode explicitly the fairness constraints as logical axioms, so you really know exactly what you put into your model. It's also very flexible because you can use any counterfactual generation method as input. You can have subgroup fairness on demand, and also these subgroups, you can choose them in a way that fits the application. Then we have this knowledge extraction, so we can do this postdoc queries and provide individual level insights. And this is also something where we want to work on in the future. So we want to kind of extend these postdoc queries to suggest concrete achievable feature changes. And we also want to work a little bit more on intersectionality. So we want, which means that we want to handle multiple sensitive attributes in our counterfactual fairness axioms at the same time. Okay, and yeah, so let's do a small recap and come to an end. So what you saw today was an integration of counterfactual fairness and subgroup counterfactual fairness into logic tensor networks. You saw counterfactual knowledge extraction as a method to improve counterfactual fairness by automatically extracting fairness constraints from undesirable counterfactual explanations. And you also saw how to postdoc query a model to provide individuals insights on the outcome. Yeah, and then I thank you for your attention, and I this QR code links to our paper.
Thank you for the talk. It's very interesting. I'm curious, trying to understand the workflow a little bit better. So the counterfactual data that you have are essentially examples of people who have similar, or people or other types of things that have similar attributes but different outcomes. Is that what the counterfactual data is?
So not really. So the counterfactual data doesn't exist. So it's not something that you can extract. So there are methods where you extract counterfactuals from an existing data set. So you try to find like the closest data point to you, which gets a positive prediction. But what we did is we really looked at these causal counterfactuals, and these are generated with your data point and then the approximated causal model. So it's a new data point actually that gets generated. Yeah. But like I said, so in the pipeline, you can put in any counterfactual you want or any set of counterfactuals. So you could also use those. Yeah.
So you could provide your own counterfactuals.
Yeah.
And
so
those would be obtained manually or something like that?
Yeah. So there are different methods to obtain those, and all of these methods you can put in because it's like a preset through the pipeline then. Yeah.
And then you can detect unfair outcomes using this method, but you can also use it to compensate and to make a model more fair. Is that
So the
correct?
primary idea is to make a model which is more fair, but you can also use it as a you can also query the model postdoc to find out.
And this model that's going to be made fairer, is it going to be any model, any machine learning model, or does it have to be a neurosymbolic model or something like that?
So we used a multi-layer perceptron for this. Yeah.
Okay. So basically any neural network is going to be amenable to this method?
Yeah, I would. Yeah. So it needs, yeah.
Sounds good. Thanks. That's the questions I had.
Okay, and I still couldn't fix my camera for some reason. Sorry about that. But we received one question from the audience. What about the impossibility proofs in fair machine learning? Don't these still apply? Don't you introduce unfairness somewhere by fixing counterfactual unfairness?
So the impossibility proofs, as far as I know, they relate to fairness metrics which you cannot apply and not optimize for at the same time. As we only work on the counterfactual fairness, so only at one definition of fairness, this should not be any problem. Also, this is not any problem, yeah. So of course, if you want to input a different definition of fairness into the model, you need to decide on which one to use. So for example, the work by Wagner, they use demographic parity and equalized odds, I think, yeah. But they have two different models trained for these both of these fairness definitions.
Mm-hmm. And I think I have similar question from myself. So in the beginning, you mentioned, like, for example, for height of 175 centimeters for a male, if we change it to female, then for her, it wouldn't be like an average height, for example. But it sounds like in this, you assume that, let's say, when applying to high school, they value more this like relative position. Let's say it's not height by GPA or something, relative GPA, rather than like absolute GPA. Like, I mean, for example, 4.5 may be high for females, but average for males or something. But maybe the law school, it doesn't care about like gender, whether it's like high in my gender or low. Maybe it's more, maybe it more cares about absolute. Like, do you see what I mean?
Yeah, I see what you mean. So I think maybe it's not that clear in the case of the law school dataset, but for example, let's imagine also this dataset has something like an address inside. And if there are like certain neighborhoods where you know there's a specific race dominance and you don't change the address, then the address can, for example, maybe associate you with a gender. And for the counterfactual, what you actually do is you change with a race, as you associate this with a specific race. And if you change the race, then you also need to change the address, because otherwise the address would still link you with your true race and not the counterfactual race in a way. Does this make sense? And that's why all the causally influenced features are changed. And that's why you also do this for the law school data sets. Yeah.
Mm-hmm. Okay, thank you. We don't have other questions from audience yet, but I have a couple more questions myself. So my main question is, maybe I missed it, but I'm curious, how do you introduce all the axioms into the like neural network models?
Yeah, so the axioms are kind of introduced as a knowledge base. And the during training, the idea is that you optimize for maximizing the truth value of these axioms. So for each axiom, you kind of, during the training, you check the truth value. And then you aggregate all these truth values. You can also weight them if you, for example, want that the counterfactual fairness axiom is seen as like more important. And then you aggregate them and you get like the satisfiability score. And then this iterates, and you always try to maximize this satisfaction. Yeah. So it's kind of you put in these axioms at the start or also during training, and they are transformed into a knowledge base. And this is all implemented already by the Logic Tensor Network pipeline. So we did not implement this.
Okay. So these are inputs to LTNs.
Yes, yeah, you can input this knowledge base to the LTN.
Mm-hmm. Got it. Okay, Rodrigo, do you have any questions from your end?
Just to confirm, so the way you're incorporating the axioms, you're basically changing the loss function to include violations of these axioms as a penalty.
Yes, and that's exactly how it's done, yeah.
Now, I don't have any other questions. Thank you.
Mm-hmm. We have one more comment from audience. By the way, impossibility theorems in group fairness only say that you can't obtain perfect fairness across pairs of definitions. The important is easy to overstate. It's just a comment, not a question. If you have anything to comment, Xenia, if not.
Yeah, I mean, it's like I said, so as we only work on one fairness definitions, yeah, not a problem.
Thank you. And one very minor question I have. So could you please show your slides? I believe it was slide 7.
7. No, I guess this is not the right one.
Oh, is it this one? Yes. So how do you define P here? Is it like a hyperparameter or like?
Yeah, so you can define P as being, yeah, so you need to have a value which is bigger than 1. And if, there's a whole work on how you actually should define P, and we also tried out different values. So it kind of depends on how you, yeah, it's a kind of a parameter that you can define, yeah. And depending on how you define it, also you get different outcomes. Yeah.
But how do you define it?
How we define it, we have we set it to 2, which corresponds to the root mean square more or less. And if you set it to 1, it's the arithmetic mean. Yeah. But you can also set it higher, yeah. But for our experiments, we set it to 2 according to a paper that was already out.
Mm-hmm. Okay, and I'm curious if LTN implementation is available somewhere, or you have to develop it yourself?
Yeah, the LTN, it's actually very, very nice documented GitHub. So yeah, it's available.
Mm-hmm. And how big is your data, and how much resources needed to train this?
So it depended a little bit on the dataset side. So Compass was very small, adult really big. So for adult, it took us 1.5 hours if we trained with all of the counterfactual knowledge extraction axioms, which, like I said, they are added iteratively. So we had 4 that were added iteratively. So if we would add them iteratively, it took 1.5 hours. And for the smallest dataset, so Compass, it took only several minutes.
Mm-hmm. Okay.
And this was on a normal laptop, so not a big machine. Yeah.
Mm-hmm. Yeah. Okay, got it. These are all the questions from myself, and I believe everything from the audience. Rodrigo, do you have anything else from yourself?
I know, thank you.
Yeah. Okay, and then maybe we can stop here. Again, I'm sorry about my camera. I don't know what happened. It just wouldn't turn on. But just in case, if anyone else has any questions, you can write them in Discord. Yeah, otherwise we can stop here and see everyone next time. Thank you very much, Xenia, for joining us today and for your time.
Yeah, thank you.
Thank you. Bye.
Bye.